That's the more formal definition of it.
Say that one more time.
So if I have an object going from one point to another, the work done by that force is the same regardless of the path that you take.
Okay.
So, in the case of weight, if I have an object falling, the work done by the weight as it falls, the force times the distance, or force times displacement, is the same if the object goes straight down or the object goes through some curve. The work done by that force is the same.
So the only one that's gonna not be conserved there is the spring force?
Is the which force?
The spring force?
No, the only one that's not conservative is the normal force from the ground.
Cause if you take a different route, you might not be touching the floor.
Unless that, if that normal force were applied, about to do a bad example. Yeah, we're about to delve into calculus here. I want to avoid that.
I mean, it's gonna be better than what's going on in my head, so.
Alright, give me a moment just to think of how to, I can do the example and just hope you don't question it. Ooh, 4. There we go. Probably this up more way.
Oh, that's much better. Why didn't you just start with that?
I know, I should have. If we just spend the first half of the course doing calculus and the second half of the course applying it.
It would all make sense.
Absolutely.
Can we put in a petition for that?
Say again?
Can we put in a petition for that then?
Yeah, you can just imagine how well that one's gonna go.
Okay.
Obviously, the calculus is beyond the scope of the course, so. I'm going to resort to a really bad way of doing it.
Okay.
The list of conservative forces that we deal with are gravitational force and the ideal elastic. Everything else is non-conservative. I know it's a sucky way of doing it, but.
I mean, that helps me out.
Okay.
Gravity and non-elastic?
And ideal elastic.
Ideal.
Is ideal perfectly?
No, different context. Ideal elastic is that in an ideal spring, the spring has no mass. It can oscillate back and forth. It won't generate any heat. It won't interfere with itself. If I take a slinky, I can only compress it so far. An ideal one doesn't have that limitation. It won't interfere with itself.
Okay.
Or jumping ahead a few chapters, the ideal elastic medium will undergo simple harmonic motion.
Yes.
What?
I can do a calculus for you.
We've had our share for today. Or I have.
Typically, the normal force is not a conservative force. Because I got a marker in my hand right now, I'm applying a normal force to it. I'm gonna do work by moving it. I can move it straight up to there. Or I can do that to get it up to the same spot. And there was more work done when I did this than if I just went straight there. And so it was path dependent about how much work I did, how much that normal force did on the marker. That's what this was attempting to say.
So basically that says that normal force is non-conservative?
Right, that one is. Yes. All right, now. I have a non-conservative force here. Why is energy still conserved?
Is it perpendicular to thing?
Is what?
You say it
It's
again?
perpendicular to the motion, or?
Yeah, do the movement. If you watch the ski slope problem, that normal force there was also non-conservative, but it didn't do any work. In order for there to be a change in energy, work has to be done. And forces perpendicular to the movement do not do work. So this box is moving back and forth like this. The spring is, or the normal force from the earth is pointing up, or the ground is pointing up. It's not doing any work because it's perpendicular.
And is that only true for non-conservative forces, like only non-conservative forces?
That's true for any force that's perpendicular to the movement, doesn't do any work. So that's why this doesn't do any work.
Okay.
So now, we start back over there. The only difference is our potential energy equation. Once you establish energy is conserved, then we're left with kinetic plus potential initial is equal to that final. And we're ready now. We can do it, all of us, in unison. It's gonna be good. What's the formula for kinetic energy?
1/2 mv squared.
That was so close. Pacing a little bit off, but I heard a lot more voices. Thank you. Now, what's the formula for potential energy?
mg.
MGA?
Oh, no. Was it Penelope, your voice?
Yeah.
Yeah,
What's the proper response?
which one?
Okay. The one associated with our conservative force over here. Now, the weight is not doing any work, so I don't care what the gravitational potential energy formula is. I only care about potential energy formulas associated with the conservative force that's actually doing any work, and that's the spring force here. So what is the potential energy formula associated with the ideal elastic?
Force equals MA?
No, only if you could start there, only if you want to derive it from scratch.
Can you repeat the
Is this the
question?
1/2 K?
That one.
What was it?
It's
Not
the,
X squared, I don't know.
it's the potential, the question is, what is the potential energy formula that goes with the conservative force that's actually doing work? That's 1/2 times the spring constant times the displacement squared.
Why doesn't the displacement get a little thingy? Where is it supposed to?
It gets into a notational issue, that technically what I'm doing here is delta x, dot product with delta x. And so I'm doing a dot product here of some vector with itself.
Okay, wait, so it needs to remain in the scalar form because the rest of it's scalar?
Right, I mean, ultimately, even if I put a vector symbol right there, to me, delta x dot delta x is delta x without the vector symbol squared. So that, it's a notational thing. Ultimately, whatever the displacement is, it is, we're gonna square it.
Okay.
And the vector part goes away. This is the big thing with energy, is the fact that we're not dealing with direction. Other than, is it doing any work or not?
Are you expected to have the formula for friction memorized? Or not?
No.
Yeah, the friction.
Friction's not involved here.
For the normal force acting, the,
Oh, the elastic potential energy?
yeah.
No, I would hope that you would recognize it. I mean, if I gave you a bunch of equations, you'd be able to go, oh, okay, that's the one that's associated. It's got the K in it, it's got the spring constant.
So K is spring constant?
Yeah, in this case, K is the spring constant. K is used for a lot of things,
Okay.
but in the context of a spring, it's the spring constant. It's a stiffness constant. Basically, 30 newtons per meter says I need to apply 30 newtons of force to this in order to compress it or stretch it 1 meter. It's the amount of force required per meter in order to extend or compress. So the higher that number is, the stiffer the spring is. It requires more force to be able to stretch it or compress it 1 meter. All right, so at this point, we've got this, once you get to the formula, the question is, what can we get rid of? Some of this stuff is gonna be equal to 0. Matter of fact, I got 4 terms here. 1, 2, 3, 4. 2 of them are equal to 0.
Well, I just know first you can take out the 1/2 from everything.
Okay, we can, every term has a 1/2 in it, so we multiply everything by 2 and the 1/2 go away. Or leave them in if you like, it's like the mass in the previous problem. So what's equal to 0? Yes. How do you know that's 0? Because what? Yeah. I don't explicitly say it stops, right? I do? Oh, different problem.
Okay, my bad. Yeah, you're number 7.
It says constant,
Well, I
but
think
that doesn't mean 0.
Yeah.
you say what's the maximum of the spring will compress, so if it's compressed at the maximum, the box can't still be moving.
Yeah, it's implied in the problem that maximum compression happens when it stops. If the box is still moving, it's not maximum compression, that means it's still compressing a little bit more. Or it's already coming all the way back out. So the final speed, not a vector here, the final speed is 0. Because that's maximum, that's what happens at maximum compression. And we got one other thing that's gonna be equal to 0.
Oh, it's the potential on the other side of the equation,
Why?
because the box isn't touching it, so it's not doing anything. Like the displacement zero.
Or specifically, yeah, there's no displacement, it's just sitting there. And so all of that long thing there just boils down to whatever the mass of the box is, which was 20, times the initial speed, which was 15 squared, is equal to, over here, my spring constant, which was 30, times how much it compressed,
That's what we're looking for.
squared. That's the math problem. However you want to go about it. So if I divide by 30, 115, so what's this? 150 is equal to delta x squared.
Would you just square root that?
Then now you square root it, then you get 12 point something.
Oh, I don't know. But, is that saying the displacement is that?
That is how much it compressed. Yes, that's the
So
displacement.
displacement is gonna mean compressed.
In this,
That problem?
in this problem, yes. If, let's just make the problem go crazy. So the box hits it, let's say the box now sticks to the spring. It's gonna compress that far, and now when it's going to start moving back out, now you got a mass attached to it, so the mass is going to have its own momentum, so the mass is gonna carry the spring farther, and so it'll end up stretching the same amount.
Are we ever gonna have questions like that?
Say it again?
Are we ever gonna have questions like that?
I haven't in the past, but why not?
Oh, gosh.
Could you just step a little bit that way? Thank you so much.
Sorry about that.
Could you actually, I'd like to take a picture of the board if I can. Thank you.
Why don't I just
So you're,
make myself scarce?
So the second part that you crossed out that you said was 0, is that whole equation, the K with displacement squared, but not the I?
Whoa.
But,
I'm confused. by
Yeah, how
that.
did you get 150?
20 times 15 squared divided by 30. Did I make a mistake? I did it in my head.
Yeah.
It's 150?
I got 12.35. Why rounded, but.
Wait,
All right, so I think there's two questions on the floor here. Hope, what was your question first of how did they get rid of stuff?
No, just how you got rid of the last thing you got rid of. I understand why you got rid of mv squared on the right-hand side, just what you got rid of on, yeah, that one.
I got rid of this one because before this is initial, this is before it hits. The spring is sitting there in its natural position. So this is 0.
Okay, but the i's also canceled with it,
Well, this piece right here is 0, so the whole term
the whole,
goes away.
okay.
Yeah, I wasn't necessarily canceling out.
I got 150.
I guess with the 1/2, I canceled it out because I divided or multiplied everything by 2.
By 2,
The second slash was saying the whole term is 0, so I'm
right,
making the whole thing go away.
okay, I understand it, thank you.
And then, I guess we have a number here. The big question is, what are the units?
Meters?
I hope so. Now, you could track units as you go through it. That's the hard way. Or you could go, wait a second, I'm trying to figure out some length here or some distance that this thing compresses. As long as I'm starting with international standard units, I better end with international standard units.
What's on the other side?
I don't understand how we got 150.
All right, so the math piece here. Let's get rid of the smartest problem.
Maybe my calculator just isn't doing it right.
So first you do this, there are several ways of doing it. If I do the left side, that's 20 times 15 squared. 15 is the only thing that's being squared here.
Okay.
So that's 225 times 20.
That's
Or-
where it was messed
Yeah.
up.
I see your point now.
She was times and the two numbers.
The
was
whole thing.
That's what
Ah.
I did too at first.
Yeah, only the 15 is squared.
Okay.
Other questions?
Can I take a picture of it again now the March problem is gone, so I don't confuse myself of what's like involved?
All right, so since we're at this point right here, what video would have been helpful for future generations or the next time I teach 110? What would have helped you?
Can you introduce the equations in class, so we can ask you questions about whether or not we understand them?
You want me to write down the equations?
Yeah, like to introduce the equations in class so we can see if we understand the concept, like,
And how to apply them.
so we can, yeah, cause like with, number 3 with the rest energy, I'm a little bit confused on how to use the E equals MC squared.
Okay. Because that was just a straight up, I gave you the mass and asked you what's the rest energy.
Yeah.
So what's the mass?
Is this number 3 on 7?
Yes.
Yeah.
That was 4.5,
40 kilograms.
40 kilograms, all right. C is the speed of light. What's the speed of light?
3 times 10 to the 8.
You round off, Nick? There is an exact number, but this is good enough. 3 times 10 to the 8 meters per second squared. And so it's 40 times 3 times 10 to the 8 squared. So 40 times 9 times 10 to the 16, which is 360 times 10 to the 16. 3.6 times 10 to the 18. primarily, once you recognize this is speed of light, and then you look it up. Calculator exercise, and then, no, you just put it at the end.
You got a 16 because you did 8 times 2.
Yes, when you have an exponent like that, so a number raised to an exponent raised to another exponent is you just multiply the exponents.
Oh, I thought it was 0 because we just weren't dealing with rest energy.
It was an homage, it's, yeah. It was acknowledging that there was one other one. I viewed it as just a quick calculator exercise. It was not meant to confuse.
No, I'm very confused.
Calculator.
And
It's
if
a
we-
bunch of energy.
And if we put it in that form, would it be fine? Like, we don't have to actually multiply it?
Yeah, scientific notation and fine, whatever the calculator presents. I would even accept 3.6, that form, which some calculators give you that form.
I still have no idea how we got from 3 to whatever you have on the board.
From here to here.
No, all of it. Where did all the letters and numbers come from?
Alright, so the mass was given in the problem.
Okay, but where did this equation come from?
Yeah.
I know there was a link in one of the videos where I talked about it.
Yeah, I don't think you ever introduced it other than rest exists, but we'll ignore it.
Oh. Good.
That's
Okay,
why,
that
that's
probably
why
would've
we
been
did
helpful.
0.
Can we go over it?
Or,
Good.
what's the right?
And- Alright, so the whole thing about rest energy, and rest, not everything has a mass. And I'm not talking an ideal rope, I'm talking in reality, light itself, the particle of light called a photon has no mass, and there are a couple other massless particles. These are particles that travel at the speed of light. I've done the derivation in class, not for 110, I would not subject you to it. I've done the derivation with a 252 class, it's about a 3-hour derivation, but ultimately you end up with the equation E equals mc squared. That m right there does not have a little sub-zero on it. Part of this is the implication that